seminar. So, uh, Professor Shohei Watabe will be giving a talk on the quantum annealing. So title of his talk is penalty-based and constrained quantum annealing under noise. So Watabe-san, so you have a roughly 20 minutes talk and also the roughly 10 minutes discussion, something like that. So, but it's almost up to you. So please start, Yasumina.
Thank you for the introduction. And good evening and good morning, everyone. My name is Shohei Watabe, and I'm from Shibaura Institute of Technology. And first of all, I would like to thank the organizers for giving me the opportunity to present my research. And today I'll be discussing our recent work on the benchmarking of penalty-based and constrained quantum annealing. And the contents of this talk can be found in the arXiv. And this work is done by collaboration with Ryota Igata and Myonsuk Lee and Yuya Seki, Yuta Mizuno, and me. So the combinatorial optimization problem is ubiquitous in the field, such as smart energies and smart grid and AI and the traffic fraud, finance, economics, and etc. And there are many efforts to solve these complex combinatorial optimization problems, such as drug discovery, finance, and traffic flow by using novel techniques. And the quantum annealing offers a promising approach to solve these complex combinatorial optimization problems to solve ubiquitous problems behind our societies. And these kinds of problems are known as the problems that are hard to solve, such as NP problems. And these problems often involve finding optimal solutions and a set of constraints. And this type of problems involves traveling salesman, knapsack, rough partition, and so on, and which can represent various LP complete and LP hard problems. And as illustrated here, these problems are modeled using the Ising problems. And for example, I explained the penalty-based quantum annealing using the graph partitioning problems, and the Hamiltonian is given here, and the sum of the HA and HP. And HA represents the penalty terms, and HP represents the problem Hamiltonians. In this case, which is the number of, represents the number of edges. And so this penalty-based quantum annealing, PQA, so there's a merit and the demerit. So pros and cons of the PQA is as follows. So one is this PQA can be mapped to an unconstrained problem. And this mapping is completely a kind of the classical way. And the cons is this PQA is hardware inefficient. So this penalty term causes all-to-all connections. So this is hardware inefficient. And this penalty term has a coefficient A. This gives additional artificial energy scales. So this is not inclusive in the problems. So this is a feature of the penalty-based quantum annealing, and or this is widely so the penalty-based combinatorial optimization problems for the Hamiltonians. And in 2016, an interesting approach proposed. So this is a we call the constraint quantum annealing CQA. So CQA is as follows. So I take the example for the graph partitioning problem, and for the CQA, the total Hamiltonian is given by this. H prop is a problem Hamiltonian, so this is a problem Hamiltonian for the graph partitioning problem, and HD is HD CQA is a driver Hamiltonian for the CQA, and so this driver Hamiltonian is specific and completely different for the penalty-based Hamiltonian. The driver Hamiltonian in the PQA is given by the sum of the sigma x step. So driver Hamiltonian of the CQA is given this form, and this form is a very interesting features. So the total Hamiltonian in CQA is commute with constraint operators. The constraint operator in this graph partitioning problem is given by this form. And the C is a constraint operator, and the sum of sigma z is the constraint in the graph partitioning. And we use the set of the basis and the state of the basis, and this is a eigenstate of the constraint operator, and the eigenvalue is a number that determines the constraint. And this constraint operator is given by the sigma z, and this constraint operator can be commute with not only the problem Hamiltonian, but also with the driver Hamiltonians. And if we prepare the initial state of the constraint quantum annealing is that satisfies the constraint operator given by this form. So during the quantum annealing, the state is confined in the constraint-satisfying subspaces. So this is completely the quantum phenomenon to confine the constraint subspace. And in contrast to the penalty-based quantum annealing, completely different from the penalty-based quantum annealing. So the initial state, the ground state of the driver Hamiltonian does not necessarily satisfy the constraint. So that we want to satisfy. And so in the CQA system, so the ground state, initial state is chosen to as for example, the ground state of the driver Hamiltonian with the penalty terms. So if we choose this ground state, so the initial state satisfies the constraint, and also the ground state of the driver Hamiltonian. This ground driver Hamiltonians. And if the initial state is an agent state of the constraint operator that satisfies constraint, the state remains with the constraint satisfying subspace during the entire annealing process, because we choose the Hamiltonian is commute with the constraint operator. And this CQA can be applied to the graph partitioning problem and the graph coloring problem and so on. And The good feature of the CQA is as follows. So this is an interesting intrinsic concept approach and hardware efficient. So there's no penalty terms. So we do not need to prepare the all-to-all connections. And we do not need the penalty Hamiltonian. So the CQA is the absence of the additional energy, artificial energy scale. And we can only focus on the constraint-satisfying subspace. So we can use a reduced Hilbert space, so which is efficient for the simulation. And also, as earlier studies explained, that the CQA can be opens a larger energy gap because it uses Hilbert subspaces. So here is the energy gap during the additive process, and the blue line is a constraint QA, CQA, and red is a penalty based, and so CQA is the opposite wider energy gap. And we expect that the CQA is a good performance. And the motivation of my study is the CQA is as follows. The CQA is an intrinsic quantum approach to satisfy constraint. However, the real quantum devices, such as the systems, are inevitably subject to the environment noises. And the noise causes the quantum state to drift out of the constraint-satisfying subspaces. And our question is, can CQA maintain its efficacy in the presence of the noise? And then we take the benchmarks of the PQA and CQA in absence and also presence of the noise. So this is what we do in this work. And the method is as follows. We use 8-node graph partitioning problems and prepared 100 random instances of the 8-node graph partitioning problems. And annealing time and the penalty strength is by this. And solve the Lindblad master equations. And D is a Lindblad superoperator. And we take the Lindblad jump operators 3 models. The phase flip models, phase flip noise, and bit flip noise, and the depolarized noise. So here is a fidelity of the success probability, and ABC, panel ABC is a result of the PQA, and ABC from A to C results for the depolarizing noise, bit flip noise, and phase flip noise. The vertical axis is a fidelity success probability, and the horizontal axis is annealing times. And the panel DEF is a result of the CQAs. And the depolarizing and bit flip and phase frequency. The blue is a no, the results in the absence of the noise, and orange is a weak noise, and green is a stronger noise. And we can find that the large fluctuations in the CQA in the absence and also presence of the noises. And for the bit flip and the depolarizing noise, the success probability apparently decreases here and here in the latter stage of the annealing, particularly for the PQA system. And here is a fidelity and for the instantaneous ground state. For the PQA system, for the PQA, the fidelity requisite decreases as the system approaches the minimum energy band. So this is around here. There's a switch from the driver Hamiltonian to the problem Hamiltonian. And for the CQA, so we miss the instantaneous ground state after half of the annealing time. So the reason is as follows. The fidelity exhibits a sharp declines after the dominant contribution of the Hamiltonian shifts from the driver Hamiltonian to the problem Hamiltonians. And the solution of the CQA does not necessarily correspond to the ground state of the problem Hamiltonian. So this is the reason why we missed the instantaneous ground state of the problem Hamiltonian. But this is no problem for the CQAs. And so here we discuss the noise strength dependence of the success probabilities. And as expected, the success probability decreases monotonically with the increase of noise strength across all noise models, the polarizing and bit freak and phase freaks. And weak noise regimes and the PQA outperform CQA are slightly outperform CQA in terms of success probability in the average. In the for relatively strong phase freak noise case, the CQA, so CQA is a red price, so CQA achieves a higher success probability than the PQAs. However, so the success probability is very small in these regions. So the overall success probability remains very low, and this is not good for both for the PQA and the CQAs. And here is a success probability scatter plot, results of the success probability scatter plot. And here, the horizontal line is a CQA fidelity, and vertical axis represents the PQA fidelity, and solving the same problem, and 100 random instances problems. And panel A is a depolarizing noise results, and B is a bit flip, and C is a phase. So blue is in the absence of noise. In this case, we can find that the CQA performance becomes so in the presence of the noise. So, for example, so green regions and the CQA performance becomes more substantial. So the PQA is better. And the only exception is under the strong phase flip noise case. But the success probability in both PQA and CQA is worse. And another interesting point is the absence of noise. For the CQA, the success probability exhibits substantial variabilities. So from almost 0 to the success probability is almost 1. So it's a very wide range of success probabilities. On the other hand, the PQA, the success probabilities are consistently estimated to exceed about 0.6. So it indicates that the PQA shows a relatively stable performance. And so the result, so one point is CQA is not always superior to the PQA. And however, we suppose that the CQA has a wider energy gap. So we discuss the relation between the performance and the energy gap. So this is a plot of the minimum energy gap ratio and the fidelity ratio. So vertical axis shows the fidelity of the CQA over fidelity of the PQA, and the horizontal axis of the energy gap of the CQA over the energy gap of the PQA. So region 1 is represents the CQA is superior to the PQA with wider energy gap. This is our expectation region, expected region. And the region 2 is the CQA is inferior to PQA with smaller energy. This is also we expect. And on the other hand, we can find that there's a regions. This represents the CQA is inferior to PQA with, even though the CQA has a wider energy gap than PQA. So this demonstrates that wider energy gap does not guarantee the higher performance. So one of the indicator of the quantum annealing is adiabatic conditions, and this replaces, and we expect the wider energy gap is a good, but it is also important for the matrix element. And this importance of the matrix element is recently discussed by the Ayasaka, Imoto, and Matsubaki, and Kawabata. And so this region, even though the wider energy gap in the PQ CQA, but the performance is not good for the CQA. And finally, we discuss the leakage from the constraint-satisfying subspaces. So this is a plot of the projection fidelity, and the projection fidelity is given by this. And the PC is a projection operator to the subspace, the state of which satisfies constraint. And so for the PQA case, so the Hilbert space, so we use this entire Hilbert space, and during the quantum annealing process, the state is becomes close to the approaches to the solution state that satisfies constraint. So the projection fidelity increases. And on the other hand, in the CQA case, the starting point is initial state is satisfies constraint. So the projection fidelity is unity. And then if there is a noise, such as a depolarizing or the bit flip cases, the projection fidelity decreases, which means it shows the leakage from the constraint subspace. However, interestingly, in the phase flip case, so exactly it shows the exactly absence of the leakages. So this is because the constraint and the density operator that is obtained from the Lindenblatt cluster equations with phase flip noise can commute with each other through the annealing process. So this can be analytically shown. And if the initial state is a pure state that satisfies constraint. And similar discussion of the leakage of the simply preserved subspace is also discussed in the XY quantum alternating operator, and that's under the problem noises. So surfaces here. And so this is a one interesting part is the CQA and constraint quantum annealing. So the phase flip, so to summarize, the phase flip error is completely irrelevant to the leakage from the constraint-satisfying subspace. And this fact is very interesting because cat code is useful to confine the constraint-satisfying subspace because cat code exponentially suppresses the bit flip errors while the phase flip error scales linearly with the cat sizes. So bit flip error is bad for the CQA, but cat code suppresses that bit flip errors. And cat code is a very useful things for constrained subspace. So this is a summary of this talk, my talk, and we systematically evaluated the performance of the penalty-based quantum annealing and the constraint quantum annealing. And CQA does not always outperform PQA, even in the absence of noise. And in the absence of noise, PQA demonstrates relatively stable success probability across problem instances, whereas CQA is significant variabilities. And CQA suffers from substantial leakage from the constraint-satisfying subspace, which degrades its performance. Now, however, the PQA phase flip noise does not induce such leakage in the CQA. And while CQA is hardware efficient, but the PQA shows a higher performance and the future direction, interesting direction is developing error-corrected quantum annealing and autonomous error corrections to mitigate the leakage from the constraint-satisfying subspace during the annealing process. And the cat code is promising for CQA as a exponential versus bit flip errors. Thank you for listening for my presentations.
Okay, thank you very much for your very interesting and exciting talk. So now it's time for the question and comment from audiences. Any question, comment from audiences? So please please switch on your microphone and just ask your question. Okay, actually, I have a couple of questions. So, okay, I'd like to ask first I'd like to know basic point of this constraint quantum annealing. So as far as I understand, to perform the constraint quantum annealing, so we need a non-stochastic type driver Hamiltonian, right? XX or YY. So you explained some example.
Okay.
It's necessary. I mean that my question is that is it possible to perform the stochastic driver Hamiltonian for the constraint quantum annealing? So non-stochastic driver is the necessary for this constraint quantum annealing?
Yeah, actually, I don't. So no. So the question is non-stochastic. Stochastic means sigma
Z or sigma ZZ or something like that.
Okay.
It's
for the driver Hamiltonian.
Yes.
Yes. For the answer is I don't know, but there's the recipe to create the driver Hamiltonian for the constraint quantum annealing, and so we follow the CSP, we can make the driver Hamiltonian for easy. But so this creation to follow the recipe is a very hard because to find the the form of the driver Hamiltonian is very difficult.
Mm-hmm.
And the graph partitioning problem and the graph coloring problem is the example too easy to.
Okay. The graph coloring, partitioning case is we already know the answer,
Yeah.
but in
Yeah.
general, it's quite difficult, right?
Yes.
I see.
Yeah.
Mm-hmm. Okay. So, any question or comment from audiences?
Can I
Okay.
ask a question?
Yes,
Yes.
please.
Hello, I'm Haider here. Thank you for the talk. I just wanted to ask, I mean, maybe you mentioned it and I missed it, but the results you presented are for these constraint problems. I'm just curious, I mean, like just to benchmark your results, did you consider also an unconstrained problem, just to see how the results compare between the constrained and unconstrained problems? Because you focus mostly on the constrained and the penalty-based methods. But have you considered something simpler even, just to understand what role the constraints have on the results with the noise?
So sorry, I cannot catch your questions clearly. And so your question is, so please say that again. So your question is,
so the models that you considered involve constraints always?
Yes.
Did you consider a problem without a constraint and do the same analysis to see how the results are affected?
So compare with unconstrained.
Something simpler, yeah.
Yeah, with the noise and without noise. I did not. I didn't do that.
I mean, I'm just it just would be interesting to get better understanding of the role of the constraint and the noise together on the difficulty of the problem, because there's two ingredients. And
Yeah. Yes.
It's very interesting. I mean, the other thing is that you're solving the Lindblad equation.
Yes.
You're not doing like trajectories. You're solving it directly, or you're sort of sampling the distribution and solving trajectories. I didn't quite understand the method.
So what we did is to solve the Lindblad master equations. So with the Q-tip and.
Sorry,
with what?
Q-tip.
Python code, and I guess that he solves the directory, the numerical.
Directly, yeah, okay. Because it's a small system, only 8 nodes. Okay. I see. Interesting. And so the problem essentially has all-to-all connectivity, more or less.
Yes. So if we induce the penalty terms, the problem is all-to-all connection.
Yeah. Okay. Interesting. Okay, thank you.
Okay, thank you very much. Yes, very interesting discussion. So, okay, any other question? Actually, that I got a question in chat. Actually, that from Stefan. Can you directly ask a question?
Yes.
Please, yeah.
Indeed, very interesting. The question is, of course, it would depend on hardware provider giving the ability of tweaking the initial or driver Hamiltonian. Do you think any future provider will give this opportunity to users? Because at the moment, for example, the wave only accept one type, a very trivial kind of driver and Hamiltonian for the initial part. So you cannot do that on the wave.
Yes.
I agree, you can simulate it, but you cannot do that on the wave, as far as I'm aware.
Yes. So from our result, so to prepare the driver Hamiltonian for the constraint contaminated is rather efficient because penalty-based contaminating is shows a better performance in CQA, and so that there's a cost for to create all-to-all connections. And another and beyond the D-wave systems, if we create a contaminator with the cat code or something like that, in that case, we can create interesting contaminating machines that expresses a bit errors, and in that case, constraint contaminating is shows a bit, maybe shows a bit. It is useful to CQA, but the actual performance is not, I think, better because based on my simulations. Because even if in the presence of only in the presence of the phase flip errors, so the performance is of the PQA is better than the CQA. But yes.
So Stefan, it's okay. So maybe I'd like to make a comment actually that for your actually that as far as I know, the previous D-Wave actually that tried to realize the XX or YY or something like funny driver Hamiltonian. So using the superconducting qubit, but we have not yet know the actual realization of the D-Wave, this kind of the tweaked Hamiltonian. Maybe that it was not successful, I guess. So anyway, and also the as regards the cat code, the Japanese company NEC actually that try to realize this kind of the cat code based quantum annealer. So then I hope that they will realize. Yes, interesting.
It makes sense. Okay,
yes, makes sense. Yes. So okay, so it's almost time for closing this today's INQA seminar. So okay, so Shohei, so thank you very much for your very interesting talk. So okay, so let's thanks to the speaker again. So thank you very much. So have a nice day and have a nice evening. So see you tomorrow. See you later. See you next. Bye.
Bye. Thank you.